My name is Jon, and I'm a software developer for Partisia, and I'm working on mainly the MPC and zero-knowledge stack of Partisia blockchain. Today I'm going to be talking about some pitfalls in programming for Partisia blockchain, specifically the MPC and zero-knowledge stacks. I'm going to be covering the secure multi-party computation architecture, some ZK contracts, and the RustZK programming language. So this is how these contracts are structured and how you can program for them. I'm gonna be covering the RustZK compiler, how it compiles secret branching and various operations on secret shared operands. I'm gonna talk a bit about how you can optimize your program for multi-party computation and what sorts of future improvements we can expect to implement. Note that in this talk I'm gonna be saying ZK a lot, zero knowledge. We specifically mean to refer to zero knowledge computation or multi-party computation. This is not the same thing as zero knowledge proofs, as you may have heard about previously. Okay, so let's start. Secure multi-party computation in itself as a protocol technique have existed for the last 50 years. This is where secrets are secret shared, so they are shared between multiple computers, and the interaction between these computers allows us to compute on the secrets without having without any of the computers actually knowing about the secret they are computing upon. This allows us to keep information confidential and still compute upon them. Secure multi-party computation can run any computation or any finite computation. Partisia blockchain turns protocol into architecture, allowing us easy availability of running multi-party computations, zero-knowledge computations, and it makes it programmable by the common programmer. So in some senses you can see this as a new type of computer architecture, similar to how blockchains like Ethereum is a type of new architecture. It supports on-demand cloud computing, so it's scalable. Unfortunately, it requires synchronized networking. As I said earlier, it required networking between several computers at once. This makes it a bit slower than standard architectures. It requires a finite computation, and it does not support branching. We will talk more about this later on. But notably, all data is confidential in this architecture. It allows us to perform a lot of computations on data that we can't necessarily know or see. And this has a lot of benefits. Programs cannot cheat with respect to confidentiality and privacy. These aspects, the confidentiality guarantees, are enforced by Partisia blockchain and by the compiler. We will look more at this later on. Secure multi-party computation requires networking, as I said earlier. Commonly, at least on Partisia blockchain, we use 4 nodes. So these are the zero-knowledge nodes that are performing the computation. And these nodes are sending messages between each other. The more nodes we have, the slower the computation becomes, but the more confidential it becomes. So secure multi-party computation requires messages for most non-trivial operations. Currently, we only support binary multi-party computation. So this means that we need to actually re-implement all arithmetic gates using binary gates. So, for example, if we have an AND operation, this requires sending 12 messages if we have 4 nodes. So 12 messages needs to be sent between all of these nodes to actually perform a single operation. So we can quickly see how this scales up when we are actually performing an addition. This requires 64 adds, that becomes 700 and some messages. Okay, but what if we scale it up even more? Multiplications. That's 32 adds, that means 2000 ands and 24,000 messages. So you can see how this quickly scales up as you use more and more advanced arithmetic operations. Okay, so zero-knowledge contracts. These are similar to public contracts, as you may have looked at already. So public contract is a Rust program compiled to Wasm bytecode running on the block producer nodes. So all state is synchronized by the blockchain. So this is how public contracts are implemented on Partisia blockchain. Zero-knowledge contracts, on the other hand, are a bit more complicated. This is the right side of this graph is the zero-knowledge computation part. So you can see that the zero-knowledge computation is encoded as RustZK bytecode, running on the ZK nodes. So commonly you have 4 nodes on Partisia blockchain, but we could at some point scale it up to more nodes. As I said before, it becomes slower to actually run multiple nodes, more nodes, but it becomes more secure. So RustZK bytecode is running on 4 nodes separate from the blockchain. This bytecode is run by a multi-level virtual machine. There's 2 levels. There's the public computation and there's the secret computation. We will look at this in more detail. And so you can see that the user can interact either with the public contract or with the secret computation directly. And all of this, all of the nodes and all of the computation is orchestrated by the public contract. The RustZK language is a form of Rust with security labels. So on the right you can see a simple program and what operations are allowed in this program. So you can see, oh, okay, we have some input. This is a public integer. This is a bit simplified. But yeah, we can have a public input that's a public integer. We can assign this input, this public variable, to a secret. That's allowed. We can perform computations between public variables and secret variables and assign them to secrets. That's allowed. What's not allowed is to actually take a secret and attempt to convert it into a public variable. So this is a form of information flow control. So information flow control is where you have a hierarchy of information levels where agents at specific confidentiality levels is able to see everything at that level and everything below it. So for example, American security agencies may have an agent at confidential level. So that means they can see the confidential level and they can see the public knowledge, but they cannot see the top secret. So we don't really use the confidential level. We only use top secret and public knowledge on Partisia blockchain. The RustZK contract, the RustZK language is executed on a multi-level virtual machine. So you can see the upper program here. This is a sum contract or a sum program where we are summing over all of the secret variables that is available for the contract and then returning it. This code is then compiled or transformed by the upper level, the first level of the virtual machine, into the secret only subcontracts. So you can see it unrolls all of the loops and optimizes the assignments until you only get this very simple program down here, where we are just loading each variable by itself and then summing it, or adding it together and then returning it. So this is the structure of our virtual machine. And all of this is enforced again by Partisia blockchain. We are not able to actually do any invalid information flow control just due to the way that the virtual machine is implemented. The RustZK compiler is what is actually taking our RustZK code and converting it into the bytecode. So it supports a significant subset of the Rust. It supports secret branching to select. We will see more about this just in a moment. So notably, public branching is very cheap. So this is just public branching is compiled as normally, or you would expect in any other CPU, any other architecture. But secret branching is special cased because we don't support branching on secrets in the virtual machine. So instead, in order to actually support branching, to make it a bit easier to write RustZK programs, we want to support if expressions in our language, but we can't actually perform the branching in the bytecode. So therefore, we are performing a secret branch transformation. So on the right, you can see a simple program where we are computing either the then case or the else case based upon whether or not, based upon some secret, and then assigning to X. The transformation moves each of the branches outside of the condition. So you can see we will always compute then, we will always compute else, and then we will select based upon this. This has very important performance implications, as we are now unable to actually skip unimportant computations. So let's look more at this. So on the right you can see we have a computation where we are branching based upon some secret. If the secret is true, that means that we want to perform some expensive computation. But due to the transformation, we are actually moving the expensive computation out, and now we are always performing the expensive computation. So, for example, I talked earlier about the multiplications. That's a common and very expensive computation. We could imagine wanting to hide that or avoid that if it's unneeded. But as you can see, it's not really possible, at least when you are branching on secrets. So in a classical or public if branch, you would either compute the condition, you would always compute the condition, and then you could either compute the then or the else. So this allows us to bypass certain operations when unneeded. In secret branching, we will always compute all of them, both the condition, then the and then the else. So expensive operations cannot be bypassed. Okay, so how can we optimize our programs a bit? Well, we need to change the way we think. So we need to go back to the 80s. Every bit counts. All of your data types, every bit that's in a data type counts. Every operation counts. Remember back to the multiplication. If we could take our 32-bit, half that, we would suddenly see that our multiplication suddenly becomes faster. You need to think about bitwise versus arithmetic. Bitwise operations are fast, that is ORs, ANDs, XORs. All of these are pretty fast. They can be done in parallel. Arithmetic operations are slow. These cannot be done in parallel, and they can make the program a lot slower. Theoretically, both can be fast. We have not implemented this yet, but we hope to soon. And you need to think carefully about your threat model. What must be secret in your program? What can be public in your program? And move as much as possible from the secret into the public. At the same time, you need to think about what must be secret. This is very important. You cannot move things that should be secret into the public, then you lose confidentiality. So consider this program. This is the sum program I showed earlier, just with a additional division. So this now becomes an average program, or an averaging program. So individual inputs must remain secret, number of inputs are public, division is an easily reversible operation, therefore we should avoid performing the division in the multi-party computation. We should perform it in the public part of the computation, such that the computation, the zero knowledge computation, is just a sum instead of an average. So what will we do in the future? What is the roadmap? So we have following planned improvements for the ZK language. We want to support more Rust. It should be easy to reuse Rust, reuse the computation across projects. We want to add several optimizations. So we want, this is in the backend, so we want to be able to batch computations and allow faster computations. And we want to add arithmetic data types. So this will allow for much faster computations for number-heavy applications. So in conclusion, this is a sort of new architecture which requires an entirely new system of compilers and of debuggers and runtime. The compiler attempts to provide certain conveniences. This, though, allows us to write somewhat inefficient code when we are writing naively. But these two difficulties, the new architecture and the compiler, allows certain unique confidentiality guarantees that we can't find anywhere else than Partisia. Future improvements will at some point give more capabilities and more efficiency. Thank you. That was it. Have a nice day.